Hey again, it's Professor Holman, and we are going to try again with a new example writing a rate law from a proposed mechanism. So here is the new proposed mechanism, and first I'm just going to actually write out the overall reaction that we're looking at. So this is a reaction that is between H2, hydrogen, and NO, nitric oxide. And when these react, they form water, 2 molecules of water, and nitrogen, N2. All the gas phase reaction. A lot of these examples we're doing are gas phase reactions because those have been so much easier to study, and especially when looking at the elementary steps. So they're very typical looking at gas phase. All right, so here is a proposed mechanism. This was, of course, proposed by many of the experimentalists who studied these, and they determined the overall rate law, and then they proposed a mechanism that is consistent with the rate law that they figured out. So here's our proposed mechanism. In the first step, so step 1 of this mechanism, we have 2 of these NO molecules that are in fast equilibrium with forming a dimer. So that means that they've bonded together and they form one molecule, N2O2. And in this proposed mechanism, this step is considered fast. And one thing I wanted to mention about the speed of this, the speed, relative speed to each other, fast, slow, medium, whatever it might be, that is part of the proposed mechanism. So when a mechanism is written, it is written with this in mind of which one's fast relative to the other one, which one's slow, which one's the slow step. That's important. So these will always be given to you as part of the mechanism you're looking at. Okay, so step 2 of this proposed mechanism, we then have H2 coming in, and it's reacting with this N2O2 that appeared. And this forms H2O. And it forms N2O. And in this proposed mechanism, this is the slow step. And then after this, in step 3, this is a 3-step mechanism. N2O reacts with H2 and forms N2 and H2O. This step is fast. Okay. I also wanted to just include on here, since we're already we're writing out these steps, that each one of these has a little rate constant associated with it. So this step 1 we'll call K1, and the reverse, since this is a fast, I'll put fast equilibrium, although we can tell it's an equilibrium because of the back forth arrows written here, that the reverse is a K-1. This is step 2, so this rate constant K2. Step 3, it's K3. Okay. All right, so then we remind ourselves, we're going to write out the rate law that's consistent with this, and so that we remember that the slow step, the rate law for slow step must be consistent with the overall rate law. So the rate law that we come up with by basing it on the slow step should then be consistent with the rate law that was determined experimentally, and we will find that it is. All right. So we're going to start out with thinking about the slow step. So our mini rate law for step 2. Okay, so we check out the slow step here, and we see that the rate is going to be, and that would be the rate for this step 2, will be equal to the rate constant for that step, which is 2, and then we get to multiply it directly by those molecules that are involved in step 2. And so that will be H2 and N2O2. Okay, so at this point we look at this and we say, all right, is this a viable rate law? Are we done? And this is where we want to do an assessment of what's appearing in here. Do we just have products, reactants, or catalysts? And so far we haven't considered catalysts, so we're not going to look at that. But we are going to look at intermediates. Okay, so we look at this mechanism here, and I'm going to change the color so we can point these things out better. And we see that, I'm going to scroll back down. Here we have our overall reaction. We see we have H2, we have NO, H2O, N2. And right off the bat we see, okay, we have this molecule here that was formed, and then we see in a later step right here that it disappeared. And so we can say, all right, this is an intermediate. Do we see any other intermediates? Yes, we do. Okay, so here's another one. I'm going to change the color. Here's another intermediate. Okay, so there's that intermediate. Whoops, sorry. Okay, so now we just check out this mini rate law again, and we see, all right, here is this intermediate that we identified. This is not allowed in a rate law. Okay, it's an intermediate. All right, so that means we are probably going to have to do some substitution. So this will be similar to the other example that we've done. And so this is where we go back and we look at this fast equilibrium that's going on in step 1. And we say, all right, we've got this fast equilibrium, and so we can recognize that the rate in the forward direction must be the rate in the reverse direction, and that we can write the rate laws in each of those directions, and hopefully that's going to allow us to isolate this intermediate and then substitute. So we see this forward direction. 2NO is going in the forward direction. So this rate 1 then, what will that be? We've got K1, and we have NO showing up there, and there are 2 of them, so that gets squared. All right, and then we have the rate in the reverse direction, so this is going to be going backwards, so K minus 1 is going to be involved with that. This is the reverse reaction, and we have that intermediate N2O2. So reverse reaction, K minus 1 and N2O2. All right, and so lo and behold, we have found a way that we can express concentration of N2O2, this intermediate, in terms of other things that are allowed to be in the rate law. And so now we are going to substitute. Into there, everything else. So we do have to solve for N2O2. Okay, so we'll divide both sides by K minus 1. You're going to see things again and again. It's going to be very consistent as you do more of these kinds of substitutions. So here, when you have a fast equilibrium, you often see this K1 divided by K minus 1. In this case, it's NO, and that's squared. So you're going to substitute this in to right there. Okay, so the result of that then is and notice how up here I had rate 2, and now I'm just writing rate, because now I'm looking at the overall rate law, which is going to be equal to the slow step. But I'm lazy, so I'm just going to stop now since we are talking about overall rate law. And so we have a K2, But we're also going to have these K1s. I like to cluster them all at the beginning. So I'm going to put our K1 and our K2 together and our K minus 1. So all of our rate constants are together. And then we have that H2. And now we're substituting in this NO. And that was squared. Squared. All right. And there is our rate law. Based on trying to scroll up, based on that mechanism that we had up there that was proposed. All right, so thank you. Hopefully that was helpful.